response curves, what you see here, and the 5 example parameters for compounds show that cortex in green and isoglutide response in red are somehow different. If I add the response of hippocampus, for instance, I see that those isoglutide neuron responses are more likely and more similar to the fast hippocampus concentration response. So it's a matter of what you compare with each other. So here I show a physiological similarity to hippocampus activity patterns and also a functional response pharmacologically to hippocampus. This is also relevant for seizure prediction, as in the current seizure prediction assays are also used at massive sample sizes. So we have used also this kind of screening approach. Besides what we have tested in cortex already, we have also a selection of seizure respective compounds tested in isoglutide neurons. We have also tested the botulinum toxin, which is a measure for synaptic connectivity, because it destroys synaptic connections. And what we see here is that we added up 28 days in vitro in pico to nanomolar ranges, which is very high concentrated, of course, but here what we see is that the synchronicity actually is abolished by botulinum toxin, and this in a concentration and time-dependent manner. And we see a very high readout in synchronicity describing parameters, even at the 10 picomolar range, so showing that it's a very sensitive readout to investigate synaptic and polysynaptic connections which are present in the isoglutamides. Coming from this characterization now to the application of seizure prediction. I start with the problem, and that is seizure liability of standard of care drugs at the market at the moment. And there's this paper from Vermeulen and Lindbeck who have described the seizure liability in reverse drug reactions. You see this list of compounds and drugs and their seizure liability at market. So we certainly want to avoid this with novel drugs, and therefore we need in vitro screening assays, and at the moment one assay is the hippocampal size assay, and we want to replace that also in the real world. We are replacing with reduction of animal. Now if we test a seizure-genic compound, which Dr. Anson was also referring to, petrotoxin and GABA-receptor blocker, we see the increase of synchronicity and regularity, and we even see ictal-like effects. So there's a hyper-excited activity, increased regularity and synchronicity, which is needed to predict seizure. What you see here is the selection of compounds we used to calibrate the system for predicting seizures in vitro. The top row is a selection of known seizure-inducing agents. They are all excitatory. You see the spike rate as a readout. And the bottom part is 3 compounds which are also excitatory but not seizure-genic. So we want to compare the phenotypic differences between these 2 groups of compounds to actually identify a measure which is very predictive for seizures. Now if we go just from the excitatory spike rate readout, all those compounds are excitatory, but they are very different in terms of their phenotypic profile in several growth structures, oscillatory, synchronicity mechanism. Now we use this phenotypic difference, which are very distinct in several growth parameters, and perform a classification using this artificial intelligence method I was referring to before. And what I can show here is that those 2 groups, they separate very nicely, and this separation can be then used to investigate unknown compounds. Those unknown compounds, for instance, are PET compounds like alpha-germorine, neuropeptide, or MCH2 compounds. These ones are all excitatory, but they are safe because they were classified in a concentration response way into the non-seizure class. So if you have a seizure-genic compound, it should end up with higher percentages at the right-hand side. And this is actually the case for 2 compounds which induce seizures. see that AMPA or glycine are also acetylcholine classified seizure-genic class. So this is a two-compound validation. How does it do with marketed drugs? And this is what you see here. The therapeutically relevant concentration range is highlighted in green, and the predicted seizure risk in our assay is highlighted in red. You also see the seizure risk from literature in terms of these asterisks here, or here in terms of percent values from the Cornelian paper. What you hopefully see is that there is an overlap of concentration ranges used clinically and found in patients' brains, and the seizure risk predicted here in vitro. So we correctly classify those compounds, and eventually, if we correlate that with between our in vitro prediction and the percent of seizure risk in men, we see an interesting correlation that clozapine has an 88% predicted in vitro, with 9% in men, and it's going down to haloperidol with 50% prediction to 3%. So that's the beginning, and donepezil has sort of the lack of seizure prediction, although there are seizures predicted for cases in men. But we should not forget that donepezil is also inducing seizures. That seizures are also symptoms of dementia, so it's difficult to split that apart. So we are able to use this visual liability prediction in mouse cells. Now, how does it do with the human cells? And we did the same assay with the isoglutamineurons from CDI, used the same panel of compounds, and see the same concentration response profiles between those compounds. So all are excitatory, and we even see the same prediction matrix here between mouse and human. So they perform as good in terms of seizure prediction calibration. And if we now investigate the selection of unknown compounds again, what we see is that they also predict the seizure genicity for acetylcholine, naphthalene, or naloxone. And if we compare that between mouse and human isoglutamineurons, they actually can perform better and predict more seizure risk, or equally than mouse cells. So this is where we need further investigation how the differences are. But what we can say is that those cells are very nicely suitable for this prediction of seizure in vitro, and that comparing them with a reference model is very effective. Now, what I've shown you today is that the MEA screening combined with multivariate analysis allows the phenotypic screening of different neuronal cultures, consistent with screening compounds and drug discovery pipelines, and it allows the quantifying of maturity on a functional basis. And this is very important to stress the quality of human IPS neurons, especially that those cells which we have from CDI show a very mature functional activity with synchronized activity patterns, which can be used for screening, have a really high yield in terms of high throughput screening applications, and they show this biological relevance, like that a dopaminergic culture is most similar to ventral midbrain of mouse or hippocampus of glutaminerone. We need the phenotypic comparison between non-seizure and seizure-genic compounds to predict most effectively those seizure liabilities in vitro. With machine learning, we have applied here classification that allows this prediction in mouse and human neurons. And by doing that comparison, we see actually the value of the human cells, because we not only use them to replace and refine them, but they might be even more predictive than the current mouse models, which needs to be elucidated. With this, I want to thank you, and we are certainly open for questions.
All right, thank you, Ben. Excuse me. So the questions now, for those of you that have asked questions or typed them in, we have the isoglutamarin product manager, Dr. Kevin Olstrom, at a different site, who will read off some of the questions for us. So, Kevin, are you there?
Yes, I am, Blake. Thank you for the presentation from both you and then from Ben. That was very informative. So we have several questions, but there are some that if those still that are listening want to still submit them, we will definitely ask that to Blake and Ben. But so for one of the first questions that we had, and Blake, you kind of touched on this with the single cell gene expression of the gluteneuron, but the question was how does CDI assess the quality of their iPSC derived neurons?
Okay, thank you. We do that in a variety of ways. One is through marker expression to confirm the identity. We also have viability metrics to ensure that the culture after thaw is viable and we just don't have a bunch of half-alive cells or half-dead cells. And then last, definitely not least, we qualify each batch through that single-cell marker analysis as well as through functionality and the formation of the synchronous activity on the NEA. So each batch is QC'd in terms of viability, identity, and functionality.
Okay, all right. Thank you, Blake. Another question just regarding the culture and the timing of the activity development within the gluteneuron. The question is, how long should the cells be in culture before they start to fire action potential, and how long before they are synchronized?
Maybe that's a question which I can answer. So we have screens in gluten neurons between 3 and 35 days. And to address this at the time point, we need a synchronization. So after 3 to 5 days, they are already active at several electrodes, but they are not synchronized. And that synchronization starts at 14 days, and we usually use those cells between 18 and 21 days, because there we have them synchronized robustly and all well. But they can certainly be used also at 35 days or so.
Okay, thanks, Ben. And then another question, and this is pertaining specifically to a part of the CDI presentation, but then I'm sure, Ben, you can speak on this as well. But the term network velocity, could either of you just elaborate on the meaning or how does one use that value to interpret data?
Kevin, you have stumped me. So network velocity comes out of one endpoint from the suite of endpoints that Axon provides in the neuromedicine tool. Again, I believe it is a measurement of how robust that network activity is. So whether or not you've got a few electrodes in synchrony, or whether you've got a strong, high level of synchrony across the well.
All right, thank you, Blake. So then a question regarding excitotoxicity. Has CDI or has NeuroProof looked at excitotoxicity in the context of leading to neurodegeneration? So said another way, has CDI looked at the excitotoxic response of various compounds?
Maybe I can answer that from our NeuroProof perspective. So we usually screen compounds with a very high molar range to see when the compounds actually kill off neuronal activity. So we know that the loss of active electrodes is linked to with cellular health. Maybe if you correlate MTT cytotoxicity assays with the number of electrodes that gives so high glutamatergic agonists at higher concentration, they tend to decrease the number of active electrodes and therefore also the cellular health. So that's what we can say, that this is then a readout where we can use the number of electrodes as a measure to look into cytotoxicity, and the activity drops down also. I had one of the slides here. Blake, you want to add?
Yeah, no, similarly, we've done some work on excitotoxicity within CDI, as well as other customer sites. There was a poster presented at the 2017 Society of Toxicology meeting by one of our customers that delves into that. So we do see the cells being used as a model for excitotoxicity, as well as seizure-genesis, and feel free to drop us an email and we can follow up in detail on that.
Okay, thank you. So sorry, was there a question there?
No, just clearing my throat, sorry.
Yeah, so another question then, has the gluteneurons and the general MEA approach to looking at electroconductivity been used to investigate synaptic plasticity? And if it has, are the mechanisms similar to brain lysis?
Well, that's a real cutting-edge research question. I'm going to toss it over. Do you have an answer?
Yes and no. So,
okay.
So the technology in general can be used, and there the Axion system is actually quite nice to use because we can stimulate electrodes electrically. So, and we have used that with at least primary neurons with lots of interesting results on a plasticity panels that we can see an increase of responsiveness to stimulation by compounds, for instance. And so that is not the same what you usually do in slices if you talk about LTP or connectivity measures, but it is certainly possible to use this technology in combination with in vitro cell cultures to address plasticity in an indirect way.
Okay, yes, thank you, Ben. To add on from my end, that's something that we're interested in investigating. And so, as Ben said, this is something that the Axion system